Hello, dear professor and all the rest that are watching this video right now. Today, me and my teammate that is currently acting as an operator are presenting testing and methods we use to execute our project. First of all, a quick important news time. We had a massive change of course. We transitioned from tracks to pan servo attached to at the front of our robot. And we'll now quickly go step by step about how we tested each functionality, which are reaching cells, grabbing releasing mechanism, and camera vision.
Hello everyone, so I will continue with the topic about how we managed to reach each cell with our robotic arm. Well, first of all, we used inverse kinematics, which most of us know. Basically, we considered the pan servo of the robotic arm to be located on the 0, 0 on the XY coordinates and on some height in regards to the Z coordinates, which refer to the height. And basically, in the perspective of these coordinates, we calculated the coordinates of each separate cell, passed this through the inverse kinematics algorithm, and got the servo angles, which were used to reach those cells. But of course, those were not so precise as we wanted. So we did a little bit of manual adjustment, like taking some servo angles to be a little bit higher or lower. And how we did the manual adjustment is basically we run short script, which helped us to visualize those settings using the matplotlib. And here we can observe each servo and the pan servo and the runtime, which is basically how fast or slow each servo runs. And gaining one or subtracting 1 degree from each servo motor, we managed to reach each cell with high precision. And of course, we did the repetitive testing to double check that everything is correct and right. And by doing so, we got those values for each servo, which are basically the angles in respect to the servo motor S7, S8, S9, and pump servo, which is about turning left or right. As you can see, the S9 servo in all the cases is the same, 163, and this is basically done so our gripper will be static and will hold the magnet. Therefore, there were no reason to change that.
Now let's look into how we tested our camera functionality. First, we decided to go for depth detection to detect cell, to identify cell status. Cell statuses are, if it's empty, populated with zeros or X's. But there is a lot of, actually not a lot of, but just 2 limitations with the depth detection. First one is that there is improper detection due to pieces size. Since you can observe from the picture that O's and X's are not properly detected. X is for some reason, O is for some reason seen by the depth camera as a whole, whereas it's not. Also, you can see from the storage board that some of the X pieces are not detected properly. It's mainly due to the second problem of our depth detection. It's errors due to positioning of the pieces. Since X is very small, it can be easily rotated within the cell. it can be detected in different ways, which is very bad. And let's see how we actually troubleshoot it. We decided to switch to the HSV color value detection. H is for hue, S is for saturation, and V is for value. As you can see from the picture printed by our camera, there is a small region within the cell that will be cut to see what the status is. It will be all explained in the further video.
So here's our setup for OpenCV testing. Well, we've decided to put the camera aside, so it actually looks from top to down to the playground board. Additionally, we've decided to put some cardboard inside each cell to make the distinguishment between the empty cell or filled with O or X, and cardboard has this kind of color that helps to distinguish.
Now I'll show you how we implemented testing for the cell status detection. We wrote the code that retrieves the HSV value for each of 9 cells on our playground board. Yeah, here you can see the playground board. And now let's take a look at the cell status. Here we can see the HSV values. We mainly focus on the value for each cell and how we actually make sure that those are correct. For instance, firstly, the values are in the same range for each cell, and also we run it multiple times, and we can see that the changes are not that big. And when we make some additions to our board, either with O's or X's, let's put all of them down. Click the values to change. We'll observe it now. Here you can see the changes in the value. For black cells, it's 84, 109, 63, 83, 86. And for white cells, the ones containing the white O figures, they are ranging from 253 to 255, which obviously makes sense. And if we run multiple times, you can see that the values are consistent with each iteration. Also, we before setting the thresholds, we also took into consideration the lighting issue, because now the room is pretty bright. We're suddenly in a dimmer room, and let's see what the changes are. You see the value is not dropping significantly, but still there is some change. And if we run it multiple times, we see that it's consistent. Also, there is a little problem with X's, because they're thin, they can be placed inconsistently on the board. We see that if we place it like that, the HSV value will differ from the HSV value for this cell and this and that. They are all going to be different and have pretty big changes amongst them. Let's see what those changes are. Here are the changes. You can see for the fourth cell, the value is the biggest. Since the piece deviated from the center a little bit, the region that is being taken picture of is more exposed to the background, which is this color, kind of brownish. That's why the value differs. And after running multiple iterations, taking notes of status for each cell and each of their V value, we set the thresholds. For empty cells, it's from 140 to 200. For cells containing O's, it's from 220 to up to 255. And for X's, since it's black, it's from 0 to 130.
Well, additionally, we wrote the code that will basically take the whole image of the board will, based on the corner detection, warp it, make the top-down look, and divide the board into the 9 separate cells. Well, let's try first of all to run the code. Yeah, here we can see the board itself. It has been detected. Here it is, and all the separate cells. Well, you will ask why the cells appear to be like this. We did it in such way that each cell is actually additionally cropped into the smaller region to make the HSV thresholding more precise and explicit. As you can see, for now, the buzzer beeps one time, and every 5 seconds, in the terminal, we can see all the dots. Basically, it's the matrix. It says that there is nothing in our board. So let me first of all take the one figure from the storage board and place in one random cell in the board. We can see that the change occurred, and it is showed there. Well, it basically will beep double times when it will see the changes. Let me toss in the O. Here we can see, again, O is showed there. So let's finalize with the grab and release functionality and how we achieve this. Well, basically here you can observe the tiny little neodymium magnets that are attached to each figure X and O. And basically those are limited for now. We have 2 of them, and I brought them from home, but our package is on the way to finally arrive. So also under each cardboard sheet, we can observe one regular black magnet, which is, although it's bigger than the neodymium, but not so powerful. So here we can observe the grippers of the robot, and the similar black magnet attached to the tip of its lips. As we mentioned before, we have the static value for dazed servo motor, which will basically hold this magnet during the game. And it will just attract the magnet from the top. We also taken into the consideration the polarity of the magnets, since it is crucial to attach those neodymium magnets in the same polarity in all the figures. Otherwise, you won't be able to grab the figure, and the magnets will basically repel each other. And also for this one as well, we have to take into consideration the polarity, and we will show the video how this works. And basically that's all for our presentation, and of course, how they say, it is better to see once than hear thousands of times. So we will show everything that we have taught before in the practice. Thank you.